Hey, this is a refresher on Beer's law, which quantifies how light interacts with matter. And we can use it to quantify the amount of an unknown compound in solution. We can quantify that concentration. So let's just think about it theoretically, conceptually to start out with. So if we have a cuvette with a colored solution in it, this is potassium permanganate at 400 millimolar, which is the same as zero point 0.4 molar. And we can see it's got a purple color. This is just a simulation, but it really kind of nicely shows kind of how Beer's law works. So if it's got this purple color, we would imagine that it absorbs light at a wavelength that's complementary to purple, so maybe more in the yellow range. Let's turn on our light and see how it works. So I can slide this, the slider across the light spectrum and see how absorbance changes with wavelength. So kind of as we suspected, the purple light pretty much goes right through. Absorbance increases as we get into the greens and yellows, and then it goes back down. So one thing that's really important for Beer's law is finding the right wavelength to monitor. You could actually use almost any wavelength where there is absorbance, but we want to use the wavelength with the peak absorbance just because it gives us the most signal, it gives us the most amount of information to measure. So I'm going to slide this over, and it looks like my peak is right around 524 or so, 524 nanometers. So we're going to stick with that 524 for the rest of our experiment. Beer's law itself can be quantified mathematically. Absorbance equals molar absorptivity times path length times concentration. So the path length is typically 1 centimeter for a standard cuvette, but you can imagine how if my cuvette were bigger, and we can actually play around with this a little bit, my absorbance is going to get bigger because more light is being absorbed by more molecules inside that cuvette if it's bigger. There's just more there. Let's drag it back to being 1 centimeter though. We usually use these 1 centimeter cuvettes, just a standard way of doing things. So what else is in the equation? Well, concentration is directly proportional to absorbance as well. The more molecules there are that are absorbing that light per unit of volume, the higher that absorbance value will be. We should be able to see that here on this slider. If we increase concentration, yeah, our absorbance gets bigger. Go back down to 400. So the last variable in here is molar absorptivity, and that's oftentimes what we need to figure out before we can really use Beer's law. If we know that the path length is 1 centimeter, then we can treat Beer's law as a linear equation, where absorbance is the y variable, concentration is the x variable, path length just drops out since it's 1, and the molar absorptivity can be the slope if we get the right data. So what this is telling us is that if we make solutions of known concentrations and measure their absorbances, we'll be able to derive that molar absorptivity value and then use it to quantify unknown solutions, solutions where we don't know the concentration of the compound we're looking at. So let's come back to our potassium permanganate solution here. What I am going to do is just make my different solutions by dragging the slider, and we'll be able to see how the absorbance is affected. And I'll quickly go over how to graph that data and how to get that molar absorptivity value as well. So I did a little bit of work on here already. The concentrations that I'm going to choose for my Beer's law calibration curve are 400, 300, and 200 micromolar. So we already know that the absorbance at 400 micromolar is 0.79. Absorbance is measured it's unitless, and it's the data that we get right off the spectrometer. Let's reduce this to 300 micromolar. So as we would expect, the solution appears lighter in color. There's fewer molecules there to absorb that light, and so our absorbance has dropped down to 0.59. And let's bring it all the way down to 200. At 200 micromolar, my absorbance is 0.4. So usually you would actually use more than just 3 data points, but I think this gives the idea of what we're trying to do here, so I'll keep it simple for this video. My graph kind of auto-generated here. You guys know how to make XY scatter plots, but just to kind of go over the variables again, we do have that concentration on the x-axis. It is important that your concentration is in molarity and not something else, not grams per liter, not millimolar, not micromolar. Absorbance and molar absorptivity is defined in terms of molarity units, so it needs to be converted if it's not already there. And then absorbance is on my y-axis. So yeah, you can see my graph is pulling from molar concentrations. So yeah, this is really all I need to do. Now I can put in a trend line, and that'll help me know my actual molar absorptivity. Slide this over here. Few important things on this trend line. This trend line is going to look great because the simulation is kind of perfect data. Yours might not look quite so good. But a couple important things on here. We do want to set the intercept to 0. An intercept of 0 means that at a concentration of 0, there's 0 absorbance. That should always be the case, particularly if you've blanked your spectrometer beforehand. And then we do also want to include the display equation and the display R-squared value on our charts. So my molar absorptivity is the slope of this graph. So we can see here that the value of that molar absorptivity quantity is 1.9759. And the R-squared value, that's just a measure of how well the linear trend line fits the data. The closer to 1, the better. And typically, Beer's law is a very well-constrained law. Our data tends to fit the model. So you tend to get very good R-squared values with Beer's law. If you're seeing something less than 0.9, there's probably a problem there. So yeah, now if I take an unknown solution and I plug it into my spectrometer, if I know my value for M, let's say I measured an absorbance. Let's say it's something even slightly lower than what I'm saying here. Let's say that I see an absorbance value of 0.25 or 24. We'll put some kind of not so even numbers in there. I really just have to solve for X now, and that's my concentration. So to isolate for X, I'm just going to take my my absorbance and divide it by my molar absorptivity. And that would give me a molarity of that unknown solution. So hopefully this has been helpful, and let me know if you have any questions.